logarithms are very closely related to exponents. In fact, they're kind of the reverse process. Exponentiation done in reverse really is what logarithms are about. And as such, we know that there are laws of exponents. We looked at them previously, and they actually give rise to what I'm going to call laws of logarithms. So the laws of logarithms are going to be what we're going to look at, but they come really from the laws of exponents. The laws of exponents imply what I'm going to see are the laws of logarithms. So what I'm going to do is I'm going to write down a law of exponents, and I'm going to show the analogous law of logarithms. So first of all, so I'm going to divide it into 3 columns here. So one of my laws of exponents is the fact that if I take the product of 2 exponents with the same base, it's the sum of the exponents. So one of my laws is b to the power a times b to the c is equal to b to the a plus c. Okay, one of my fundamental principles. So just as an example, we could have 2 squared times 2 to the 3 is equal to 2 to the 5. Now this gives rise to a corresponding law of logarithms, which does look quite different. And it's rather confusing how they're related, but the corresponding law of logarithms is the following. Log b of a product, I'll write m times n, turns into a sum. So this is kind of backwards almost because, well, it is backwards of course because it's logarithms, but let's see why this is true in the case I've just given. So I'm not going to prove this from the law of exponents, it's always a little bit confusing. Instead, let's just check it out in this case, shall we? So log, what am I doing? Log to the base 2 of 2 squared times 2 cubed. What does that have to be equal to? Well, it's equal to log to the base 2 of 2 to the 5. And that, by the cancellation property, or really just by definition, has to be equal to 5. But log to the base 2 of 2 squared plus log to the base 2 of 2 cubed, well, that's just equal to 2 plus 3 by definition. That's equal to 5. So these two things are equal to each other. Brilliant, we've picked up exactly the property we expect. So this is an important property because it will allow us to simplify expressions which may seem quite complicated, especially in calculus. So let me kind of give you an example involving more complicated terms. So for example, we could have something like log of, let's say, x plus 1, so I'm doing it in base 10 just to make the notation simple, plus log of 2x, so log of 2x plus 3, let's say. So can I unite these into a single expression? Well, yes, because of the sum. So the sum I know has to be equal to the product, so maybe I should write it properly. So this is going to be united together into log of the product of these two guys, x plus 1, assuming everything's positive. So we've got to make the assumption, remember, you can't take logarithms of negatives. So we're going to assume these are positive. So I suppose if you want, you could factor this out, the usual business. This would be equal to log of 2x squared plus 5x plus 3 in the end. Okay, assuming everything's positive. So This equality could be very useful, right? It may be easier to deal with this latter expression versus the first, or vice versa. But it's important you understand that you can go freely between these two expressions, assuming everything being fed into a logarithm is positive. Now, warning, classic mistake. A classic misunderstanding is the belief you can do this for sums as well. So if I do log to the base b of m plus n, it's very easy to think, oh, well, something similar happens, so maybe this is equal to log to the base b of m. So this absolutely is not true in general. No way. And we could see this with an example if we wanted. If we had, so let's do log to the base 2 of, let's say, 4 plus 4. So this is equal to log to the base 2 of 8. That's equal to what? Well, 2 to the power 3 is 8, so this is equal to 3. But if I was to do them individually, it would be log to the base 2 of 4 plus log to the base 2 of 4. And what's that equal to? Well, 2 to the 2 is 4, so it would be 2 plus 2, that's equal to 4. And then it would equal to each other. So visibly, this cannot be correct. So super important, right? This is a really important property of logarithms. And really, in terms of what you're going to use logarithms for in more advanced classes, this is one of the most important things to know. Right? You'll often be confronted with situations where you have a logarithm in an expression and you'll be expected to simplify or rearrange in some way. This is what you're going to have to use, right? Or one of these rules. So it's absolutely crucial you understand this. So the logarithm of a product is the sum of the two terms. Okay, so what other laws of exponents are there? So there is the the quotient of two exponents. Okay, so for example, b to the power a divided by b to the c is equal to b to the a minus c. So this corresponds to the following law. Log base b of a quotient m divided by n turns into a difference. It's important to get them the right way around. It's the numerator part minus the denominator part. Very important law of logarithms. So logarithms of quotients turns into differences. Let's see this in action, shall we? So let's do 3 squared over 3 cubed. So what's that equal to? It would be 3 to the 2 minus 3. That's equal to 3 to the minus 1. So the reciprocal of 3, 1 over 3. Let's work out the left-hand side and the right-hand side here. So the left-hand side is log cubed, log to the base 3 of 3. So I'm doing it base 3 because it's the most simple. Well, this now is log 3 of 3 to the minus 1. And by definition, that's just equal to minus 1. But if I had done log to the base 3 of 3 squared minus log to the base 3 of 3 cubed, that becomes 2 minus 3. That's minus 1. Perfect. They're equal to each other. Excellent. Let's do a slightly more challenging example. Let's do something like this. So imagine if I want to try to simplify in some way an expression of this form. Log base 2 of, let's say, 16 divided by 2 to the power x plus 1 in the exponent. Let's take that, shall we? So what do I know? I know this has to be equal to, it's a difference. So it's going to be log to the base 2 of 16 minus log to the base 2. So I think I'm going to have to go below here because I'm running out of space. So it's minus log to the base 2 of 2 to the power x plus 1. Okay, very nice. But now 16 is 2 to the power 4, so this is equal to 4 minus, okay, well, by the cancellation property, minus x plus 1. So I suppose if you want to kind of tighten this up a little bit more, this would be 3 minus x. So that shows you this complicated expression hugely simplifies. This is a really good example of why it's important to understand the laws of logarithms so that you can simplify potentially complex ideas. So there's only one more actually which is going to correspond to a law of logarithms, as we're going to see. It's where what's going on? So it's why I do 2 exponentiations. Okay, so a law of exponentials is b to the power a to the power c is equal to b to the a times c. So this corresponds to the following law of logarithms, not completely obvious. Log to the base b of a power, m to the n, is equal to a product. It's equal to n multiplied by log to the base b of m. So this is what it corresponds to. It's not obvious that these match up, but this is the log version of that. Okay, and I suppose for this to make sense, you certainly need m to be positive because you can't take log of a negative, or indeed can't be 0 either. So let's check why this is true, at least with a numerical example. So let's do 5 squared to the power 3 is 5 to the power 2 times 3, 5 to the power 6. I'm not going to bother to work out exactly what that is, it's quite big. And now let's work out the left and right hand side, shall we? So log the base 5 makes sense, doesn't it? 5 squared to the 3 is equal to log to the base 5 of 5 to the 6. By definition, that's equal to 6. Let's work out the other piece. 3 times log to the base 2 of 5 squared. By definition, that's 3 times 2. That's equal to 6. Bingo. So that gives you some numerical intuition for why these correspond to each other. This is really important as well. So just as an example, a bit more complicated, if I had logarithm, so I don't know what base I do, it doesn't really make much difference, but let's do log to the base 3 of the cube root, let's say. So the cube root of x to the 4 plus 1. So first of all, x to the 4 plus 1 is always positive. X to the 4 is always greater than or equal to 0, so x to the 4 plus 1 is always greater than or equal to 1, so I don't have any problems. This, remember, is equal to log to the base 3, so I'll write this in standard exponent notation to power third, right, to put it in exactly the right format. So now this becomes what? This becomes, so I don't like this too much, I should be writing this properly. And this is equal to, well, you can bring the third out the front. And you can't really go any further than that. There are no laws of logarithms for sums, right? Just as we saw in this warning up here, there's no simplification. So there's no simplification for log of two sums, or log of a sum of two terms. So here, it's very important that you understand exactly what's going on in terms of the notation. So this is a warning. An extremely common error is writing things sufficiently poorly that it's not completely obvious what you mean. So a lot of people, when they write this, will be kind of slapdash about it and will write log to the base b of m raised to the power n. Now this is ambiguous, right? It's ambiguous because of the way you've bracketed it, right? It's not completely obvious what you mean. You might mean this, log to the base b of m to the n. You might mean that, or you might mean this, log to the base b of m, all of that to the power n. That's a huge difference, right? That's taking the nth power of the entire logarithm versus taking the nth power of just the m. They are completely different in general. So this is super important. The m to the n must be going into the logarithm if you want. So just as an example of this, if I was to take log to the base 2 of 2, and then I was going to square the entire thing. Well, log to the base 2 of 2 is 1, so this would be 1 squared, that's equal to 1. But if I was to bring the 2 inside, so I don't need another bracket, well, that's log to the base 2 of 4, that's equal to 2. They're not equal to each other. So this is super important. Be very careful when you're doing this rule in particular, right? Don't write this, is what I'm really trying to say, because it's kind of ambiguous. To me, it looks most like the second case, right? It looks more like this than this. Either way, there's no log law for this, right? So you don't want to be writing it down. The log law requires this to be inside the logarithm completely. So that's the laws of logarithms. They're incredibly important. There's only 3 of them, right? Only 3 of them. And really, the middle one, so let me zoom out a bit so I've got all of them. The middle one you can get from the top and the bottom. So really there's only 2 laws. You can get the middle one by taking n is equal to -1 in the bottom example, and that gives you reciprocals to be negatives. So really the first and the last are what matters when it comes down to this. But you really should take the time to internalize these. I can't stress enough how important they are. You're going to use them a lot when you're doing difficult examples in your calculus classes and beyond.